Hi everyone. In the last class, we have discussed about the monotone convergence theorem for self-adjoint operators. Today, we are going to give an application of the monotone convergence theorem, which is nothing but existence of square root of a positive operator. We know that if a is a real number, which is positive, then there exists a unique b in R which is bigger than 0 such that b square equal to a. We call this b as the square root of a. This is the positive square root of a. Now we want to extend this result to bounded linear operators which are positive. So let us write this as a theorem. Let T be a bounded operator which is positive. Then there exists a unique bounded operator B in B of H positive such that b square equal to T. Not only that, further, if S is a bounded operator such that St equal to Ts, then we can say that B also commute with S. Bs equal to Sb. Okay, such a B we call as the positive square root of T. Such a unique B is called the positive square root of T. And it is denoted by T power R. Okay. So this is a statement of the theorem. Without loss of generality, assume that T is between 0 and identity. You know that T is anyway positive. So if T is not less than or equal to identity, we can work with T by non-T, which is less than or equal to identity. Okay. Now this procedure is similar to the construction of positive square root of a real number. Okay. So here we define a iterative method. So let us define T0 is identity and Tn plus 1 as Tn plus T minus Tn square by 2. Let's call as equation 1. So this is for all n in n. Okay. Now we want to show that this Tn converges to B where B square equal to T. So to prove this, we use the monotone convergence theorem. So first we show that step 1, zero less than or equal to Tn less than or equal to identity for every n. So let us try to look at inductively. So we know that T naught is identity, so which is positive. So T naught is positive, and T1, if you look at, that is T naught plus T minus T naught square by 2, that is nothing but identity plus T minus identity by 2. This is nothing but I plus T by 2, which is positive. Now if you look at T2, T2 is nothing but by definition T1 plus T minus T1 square by 2, but we know that T1 is I plus T by 2, which is positive, so this we can write as I plus T by 2 plus T minus I plus T by 2 whole square divided by 2. This is I plus T plus 2T minus T square plus identity minus 2T. Here you will get 4, so this is 4T, and here it is 8. So this is nothing but 4 identity plus 4T plus 4T minus T square minus identity plus 2T by 8, and this is nothing but this is plus this minus. So this is 8T minus 2T, so that is 6T minus T square plus 3I divided by 8. This is nothing but 6T plus 2I plus I minus T square by 8. We know that T is positive, 6T plus 2I is positive, and since 0 less than T less than or equal to identity, so here we assume that 0 less than T less than or equal to identity. We know that T square is also less than or equal to identity, that we have already seen. That means I minus T square, this part is positive, so sum of two positive operators is positive, hence we can conclude that this is positive. Now using the induction we can show that Tn is positive for every n in n. Now we want to show that Tn's are less than or equal to identity. So for that we have to look at I minus Tn. Next consider I minus Tn plus 1. By definition Tn plus 1 is defined as Tn plus T minus Tn square by 2. So this is I minus Tn minus T minus Tn square by 2. So this is nothing but 2I minus 2Tn minus T plus Tn square by 2, and this is equal to this is Tn square minus 2Tn plus I plus I minus T by 2. So the first term is nothing but I minus Tn by 2. So this is I minus Tn whole square plus I minus T divided by 2. We know that I minus Tn is positive, so its square is again positive, and we also know that I minus T is positive, so on the whole this is positive. So we can conclude that Tn is less than or equal to identity for every n in n. So we have shown that the first step, that is 0 less than or equal to Tn less than or equal to identity. Now we want to show that Tn's are decreasing and bounded below by some operator which is self-adjoint. Then we can use the monotone convergence theorem. So let us look at step 2. If you look at Tn minus Tn plus 1 is nothing but polynomial in I minus T, where P is a polynomial with positive coefficients. Again, this can be shown by induction method. So earlier we have shown that Tn is positive by inductive process. Now this also can be shown by induction method. Let us look at n equal to 0, that is when look at T0 minus T1, that is nothing but I minus T1 is I plus 3 by 2, and this is nothing but 2I minus I minus T, so this is I minus 2. So this is a polynomial in I minus T with the coefficient 1 by 2, and we know that I minus T is positive, so this is positive. So next consider T1 minus T2, this is I plus T by 2 minus, if you look at T2 by definition, T2 is T1 plus T minus T1 square by 2. This is T1 plus T minus T1 square by 2. Okay. So let us replace T1 by I plus T by 2. So this is nothing but I plus T by 2 minus I plus T by 2 minus T minus T1 square by 2. So this is minus of T minus T1 square by 2, and this is nothing but T1 square minus T by 2. Let us try to replace T1 by I plus T by 2. So I plus T by 2 whole square, so we can get I plus T square plus 2T by 4. So this is minus 4T, and this is 8. So we will get T square plus 2T, T square minus 2T plus I divided by 8, and this is nothing but I minus T whole square by 8. So this is a polynomial in I minus T with the coefficient 1 by 8, which is positive. So in general, continuing the same, we can actually show that we can conclude that Tn minus Tn plus 1 is polynomial in I minus T, where P is a polynomial with positive coefficients, so which is positive. That means we can say that Tn is bigger than Tn plus 1 for every n in n. So Tn's are decreasing. Now we want to show that Tn's are bounded below by an operator. This is positive for every n in n. So hence we can conclude that we can apply the monotone convergence theorem by the monotone convergence theorem, there exists some A in B of H such that Tnx converges to Ax for every x in H. So we can write this as B because we want an operator B. This is a pointwise convergence. Now as Tn's are positive for every n, so we have inner product Bx with x is limit inner product Tnx with x. This is bigger than 0 for every x in H. Therefore we can say that B is positive. See, by the monotone convergence theorem we can say that B is self-adjoint. So we can say that B equal to B star, and with this we have shown that it is positive. So we have shown that there exists a B such that Tn converges to B. So next we want to show that B square equal to T. But this directly follows from the definition of Tn plus 1. Now by looking at equation 1 we can conclude that Tn plus 1x converges to Bx, and on the right hand side Tnx converges to Bx. So if you have, by 1 we can actually, by 1 we can say that Bx is Bx plus T minus B square x for every x in H, because left hand side converges to Tn plus 1x converges to Bx, Tnx converges to Bx, and again Tn square x again converges to B square x. So from this we can conclude that therefore B square is T. Next we want to show the commutative property. So let us assume that let S is a bounded operator such that St equal to Ts. Then we want to show that B also commute with S. To show Bs is Sb. So by definition of Tn plus 1, we know that Tn plus 1 is Tn plus T minus Tn square by 2. S commute with T implies that S commutes with Tn for every n. This can be shown by induction. This is easy to show. So from this we can conclude that now Tn converges to B, so Sb equal to Bs. So this completes the commutative property of the square root. Next we want to show the uniqueness. Okay. So let us assume that there exists one more operator, say A, which has the property of which satisfy the properties as B. Let A be another operator such that A is positive, A square equal to T, and AS equal to SA, whenever st equal to ts. Then we want to show that a equal to b. So the claim, so let us take, so let us write y as a minus b x. Then if you look at a plus b, inner product y with y, this can be written as a plus b multiplied by a minus b acting on x, inner product with y. Now, so this is a square minus ab plus ba minus b square inner product with y. Now we know that a commutes with any operator that commutes with t. Now t commutes with t itself, so, and t commutes with b, so a also commute with b. So because of this reason we can say that a square x minus b square x inner product with y. But we know that a square is t and b square is t, so this is tx minus tx inner product with y, this is 0. So from this we can say that inner product ay with y plus inner product by with y is 0. So let us call this as equation 2. So now from this we can conclude that inner product ay with y is a positive number, inner product by with y is a positive number because a and b are positive. So from this we can say that ay y is 0, inner product by with y is 0. Okay. Now we can write a is a positive operator. It has, there exists some c such that a equal to c square. So as a is positive, there exists c such that c square is a, because of the result that we have proved now. That means we can say that inner product ay with y is c square y inner product with y, that is norm cy square, that is 0. So this implies cy is 0, cy is 0 implies c square y is 0, so this is ay is 0. Now similarly we can show that by is also 0. So similarly we can show that by is 0. So we have shown that ay equal to 0 and by equal to 0. Okay, now let us look at we want to show that ax equal to bx for every x. Next, consider norm of y square, that is norm of a minus b acting on x square. This is, we can write as a minus b x inner product with a minus b x, and this is nothing but a minus bx is y, a minus bx. So this can be written as a minus by inner product with x, because a minus b is self adjoint, we can bring it to the left hand side, again we get a minus by. We know that ay is 0 and by is 0, so this is 0. So therefore we can conclude that ax equal to bx for every x in h. So this completes the proof that a equal to b. Okay. So this is the proof of the existence of unique square root of a positive operator. Next we want to give some important applications of this result. let A and B are positive operators, then AB is also positive. We can show that when A and B are self-adjoint and if they commute, we can conclude that their product is self-adjoint. So if A and B are positive and commuting, then we can say that the product is positive. Let us look at the proof. We want to look at inner product ABX with X. So let us take X in H. Then if you look at inner product ABX with itself, now A can be written as A power of into A power of. So this is A power of B power of X inner product with X. Because A and B are positive, then they have unique positive square roots by the earlier result. Now AB equal to B implies square root of A commutes with B, and AB equal to B implies square root of B also commute with A. So from that we can say that square root of A commutes with square root of B. So AB equal to BA implies A power of commute with B. This also implies A B power of commute with A B power of equal to B power of A. Now whenever an operator commutes with B, now B commutes with A power of implies its square root also commute with. So from this we can say that A power of B power of is B power of A power of. Okay. So whenever AB commutes, then the square root also commute with each other. Now from this we can actually show that A power of, this is B power of A power of B power of X inner product with X. So this is nothing but A power of B power of X. So you take this other side, you will get B power of A power of X, and we know that they commute. So A power of B power of X. So this we can write as A power of B power of X. So this is nothing but norm of A power of B power of X square. So this is always positive. So hence we can say that therefore the product is also positive. Okay, so this is one of the important applications of the existence of the positive square root of an operator. So let us look at one more important application. Let T be a bounded operator on H with T positive and T less than or equal to identity. Then we have shown that T square less than or equal to identity, but actually we can prove something more. We can show that 0 less than T square less than T. Okay, so we know that T square always less than or equal to identity whenever T less than or equal to identity. Let us look at the proof. So we have T minus T square is nothing but T into I minus T. Now T and I minus T are positive operators, and they also commute, so then the product is also positive, as t into I minus t is I minus t into 2, and I minus t is, so product of two commuting positive operators is positive, hence we can see, so therefore 0 less than t square less than t, and we know that this is identity. This completes the proof of this result. Let us look at few simple examples. Let lambda 1 lambda 2 be two positive real numbers. Define t from c2 into c2 by t of x1 x2 is lambda 1 x1 lambda 2 x2 for all x1 x2 in c2. So we know that it is clearly a positive operator. Then if you look at model, so let us take, we can easily guess that square root of t x1 x2 is square root of lambda 1 x1 square root of lambda 2 x2 for every x1 x2 in c2. And if you look at if you square this, you will get t. Now since the square root of a positive operator is unique, so from that we can conclude that square root of t is exactly this operator. The matrix of t with respect to the standard orthonormal basis is lambda 1 0 0 lambda 2, and square root of t, the matrix of square root of t is nothing but lambda 1 power of 0 0 lambda 2 power of. Okay, now we can extend this for finitely many, we can take finitely many scalars lambda 1 lambda 2 so on lambda n. We can define a map from c power n to c power n in the same way. So let us try to still extend this. Let us take lambda n be a sequence of numbers for every n, and this sequence is in L infinity. So define t from L2 into L2 by t of x1 x2 x3 so on is nothing but lambda 1 x1 lambda 2 x2 lambda 3 x3 so on for every xn in L2. Earlier we have seen that the matrix of t with respect to the standard orthogonal basis of L2 is an infinite diagonal matrix with diagonal entries lambda 1 lambda 2 lambda 3 so on. So t can be written in this way. Remaining 0, and from this we can easily guess what is square root of t. So this is the matrix lambda 1 power of lambda 2 power of lambda 3 power of so on, and remaining places it is 0. That means we can say that t power of x1 x2 x3 so on, it is given by lambda 1 power of x1 lambda 2 power of x2 lambda 3 power of x3 so on. Now still we can generalize. Let us take phi from L infinity of 0 1 phi positive, that means phi of t is bigger than or equal to 0 for every t in 0 1. Look at the corresponding multiplication operator. for every f in L201. Now we can easily show that m power of the square root of m5. We know that m5 is positive. This we have already seen. So this is nothing but m5 power of, that is square root of 5. And this example we can still generalize for L2 of x sigma mu. You start with 5 from L infinity of x sigma mu, where x sigma mu is a sigma finite measure space, and do the same way. Okay, so these are the few examples which illustrate the square root of a positive operator. I'll stop here. Thank you very much.